Hello and welcome to this film, which is all about the electrolysis of aqueous substances, or substances that have been dissolved in water. Hopefully you've seen the film about the electrolysis of molten substances. This film is going to deal with why it's a little bit more complicated, why we have to consider a number of different options when we're electrolyzing an aqueous substance. And we're also going to hopefully understand how the observations that are made during an electrolysis of an aqueous substance can help us to decide what's actually going on and which one of these options is correct. Okay, and then we can write some half equations based on those observations. And then once we've covered the theory, we'll have a look at two really important industrial processes that rely on these principles, and they are electroplating and electrorefining. Okay, so we'll ask ourselves first, why is aqueous electrolysis difficult? This is from a different viewpoint to the one when we looked at it at molten electrolysis, where we were talking about the practical issues of electrolyzing a molten substance. Now we're going to ask ourselves, what is it that's a bit more complicated here? Why are there more options to consider? Well, let's think about it and think about what would happen if you electrolyzed molten sodium chloride. Well, you'd have sodium ions going to the negative electrode, and you'd have chloride ions going to the positive electrode. And we should be able to decide by now which one's going to get oxidized and which one's going to get reduced. But because we're in aqueous solution, we're also going to need to consider the hydrogen ions and the OH minus ions. And then, as if that wasn't complicated enough, we've now got to say to ourselves, well, because there aren't very many of these, actually what we're going to need to consider is the fact that water itself could get oxidized or reduced in this cell, and so we're going to need to look for some half equations where water is gaining and losing electrons. Okay, so bearing that in mind, let's have a look at this equipment here that's being used to electrolyze aqueous sodium chloride. It's talking here about what's going on at the anode. The anode, remember, is where oxidation happens, so chloride ions could come along here and they could lose their electrons and turn into chlorine molecules, except of course we'd need two chloride ions for that to happen. What else could happen? Well, hydroxide ions could come along and lose electrons, but remember, we're not going to talk about the ions of water, we're going to talk about water itself. And if we look on our data sheet and try and find a half equation where water is losing electrons, we can see that two water molecules turn into oxygen and 4H plus ions and 4 electrons. And we can see there the electrons on the right. So again, water is being oxidized here. Now, you can use the voltages to predict which one of these two is going to happen, but that is beyond the scope of the WACE course. So what we need to be able to do is we need to be able to look at what is happening at this electrode, and does it help us to decide which one of these half equations actually took place. Well, if water had been oxidized, then we would have formed oxygen. We should know that oxygen is a colorless gas, but here we've got bubbles of green gas forming. And so that should lead us to believe that it wasn't the oxygen that formed, but the chlorine, and that now tells us that it was this half equation that represents the process taking place at the anode, and not this half equation. So again, we don't have to predict which one would happen, but we do have to be able to use the observations that we would be given to decide which one actually took place. Now if we were to have a look at the cathode in this process, so now where reduction is taking place, we should know that we've got sodium ions that could gain electrons, because this is reduction, okay, and they could turn into sodium atoms, or H plus ions could come along, but remember, we're not doing them, we're doing water. So let's find a half equation with water in it, and water gaining electrons, so that can be found at minus 0.83 volts, and we've got two water molecules gaining 2 electrons, forming hydrogen, and 2 OH minus ions. Is that enough? That's enough. Okay, so again, we don't have to predict which one of these is going to happen, but we do have to make use of the fact that we would have been told that bubbles of colorless gas were forming at the negative electrode. Why might that happen? Well, not because sodium was forming, because sodium is a metal and it's going to be solid at this sort of temperature. In fact, it's going to react with the water straight away, but anyway. So we're left with the idea that, well, bubbles of colourless gas could well be hydrogen, so we can rule out this top equation and we can say, right, well, this is going to be the half equation for what's taking place at the cathode in this cell. Okay, so that's how we decide what's going on in the cell using the half equations. Now let's have a look at what applications we might put this to. And before we do that, let's consider what would happen if you electrolyzed copper sulfate solution using inert electrodes. Well, at the negative electrode you could have copper ions, or H+ ions, being reduced, and at the positive electrode you could have sulfate ions or hydroxide ions being oxidized. Now sulfate ions don't appear on our data sheet, so we're going to cross them out and pretend that they just can't be oxidized. Okay, but if hydroxide ions are oxidized, we're going to form bubbles of colorless gas, because water is going to lose electrons, it's going to form oxygen. Okay, so there's the bubbles of our colorless gas. Now what's going on at this negative electrode? Well, presumably the copper ions that are in this solution are migrating over to this electrode. They're picking up electrons, and that explains why we're forming this coating of copper here on our electrode. Okay? Now, that would be quite a good way of covering something in copper if you wanted to, but the trouble is that as soon as your solution runs out of ions, you're not going to be able to plate your material anymore. You're not going to be able to cover it in any more metal. So, if you wanted to plate something in another metal, like this pair of glasses here that we're trying to plate in gold, then we have a solution that contains the ions of the metal that we want to coat this thing with, and we can have a look on our data sheet and see that these are gold 3+ ions. Connect these, whatever object it is that you want to plate, to the negative electrode to attract these positive ions to it. Give these positive ions some electrons, and they'll turn into the metal atoms on the surface of this thing. And if we take electrons away from these atoms, because remember we've got gold here, if we can take the electrons away and turn them into gold 3+ ions, and these electrons will come round the circuit, then this gold electrode will produce more and more ions for us, and our solution won't run out of ions. So if we want to plate something, we put it into a solution of the ions of the metal we want to plate it in, and we make the other electrode, the electrode where we want oxidation to happen, so that is our anode, or in this case it's going to be the electrode that is not having electrons forced round to it, so it's our positive electrode. We make that out of the metal that we want to plate our other object in. So there's one application, electroplating. Now, very similar in principle to electroplating is the electrolysis of copper sulfate solution in order to purify copper. Okay, now here we've got a negative electrode which is going to attract copper ions. If you made this of a very thin wire of copper that you knew was very pure, then any copper ions that got deposited onto here as copper atoms would just add to your very, very pure lump of copper, and as your electrode grew you'd have more and more pure copper. If you had an impure lump of copper as your anode, your positive electrode where oxidation is going to happen, then the copper atoms in this electrode could lose electrons, they could be oxidized, they could turn into copper ions, and these copper ions could then make their way to your other electrode. So if you had impurities in this substance, let's just kind of dot them around the place, then as the copper atoms fell off this electrode and went to the other electrode, then the impurities would simply fall to the bottom of this beaker, and the impurities would end up getting removed from your impure copper, and we'd be left with very, very pure copper on this electrode. And the lovely thing about this is not only do we get a nice pure lump of copper at the end of it, but these impurities are often quite valuable. They're often things like gold and platinum and things like that. So we've removed them from the copper and we can just collect them from our cell, and we've got samples of these metals. So electrorefining, as it's called, because we're purifying a metal by electrolyzing it, we're doing it in a solution again. It's like electroplating because we're basically plating the impure cathode, we're plating the pure cathode with metal that has come from the impure anode. Right, anyway, that's it for electrolysis. Hopefully it all makes sense. If it doesn't, If you've got any questions, if you've got any comments, then please feel free to come and see me or post a comment on YouTube.